Hello and welcome to my A-level chemistry tutorial. Today we're going to be looking at some organic chemistry in the form of curly arrow mechanisms and in particular electrophilic addition. This is something you would probably come across in year 12. It's one of the first mechanisms you look at, but nonetheless it's really important. So electrophilic addition. Now an electrophile by definition is a substance that is positively charged. It's a positively charged reagent that is attracted to electron-dense areas. So as we know, electrons are negatively charged, so an electrophile you'd expect to be positively charged because it'd be attracted to electrons, and as we know, positive and negative charges attract. So electrophile must have some sort of positive charge. The reaction we're going to look at first is going to be halogenation. That's the one we'll start with, and in particular the reaction between ethene and bromine. Yep. So I'm going to draw it out, displayed formula, so we can carry out the mechanism. So here's ethene, and there is a molecule of bromine. Now, where we're going to start in this mechanism is, we've got ethene and we've got bromine. Now ethene, of course, we know has a double bond, as this is an alkene, and this double bond inside it is very electron dense. And that's purely because there's a lot of electrons surrounded in there. All these electrons are in this double bond. And what that does, that distorts the bromine. Because these electrons are attracted to that bromine thing. And so it kind of distorts the electrons and moves the electrons in this covalent bromine bond towards the bottom bromine. So what you end up with is a slightly positive charge at the top and a slightly negative charge at the bottom. So one of the bromines has a slightly positive charge, one of the bromines has a slightly negative. We call that delta positive and delta negative. So the electron density is kind of pushed to the bottom bromine. And so what that does, that allows this electron dense area to be attracted to this bromine that's not got much electrons. And so the way we start the mechanism is an arrow from the double bond to that bromine. Yep, because that attracts to that. And then what happens then is we want this bromine to detach and join that. So we have to draw another arrow from this covalent bond going towards that bromine. And that's your second arrow that you have to draw. So one arrow from the double bond to the first bromine, that's got a slightly delta positive charge, and then an arrow coming away to the delta negative bromine. And what that does, that then forms what we call a carbocation. So what happens is the double bond breaks as it's got a bromine now attached to it. So we'll redraw this now with a bromine. But now there's a carbon that doesn't have four bonds, and what we call that is a carbocation. And so what a carbocation is a carbon that has a positive charge, in simple terms. Yep, and then we put that bromine on there, and then we've got a bromine left over. Now this bromine, you've got to have a negative charge on it and also a lone pair of electrons, as these double-headed arrows show the movement of two electrons. So please make sure you draw double-headed arrows, as you will lose marks in an exam if you don't. And then the next step is, what happens is, this carbocation, as it's a positive charge, it lacks electrons, and then this bromine has got a lone pair, and so we draw an arrow from the bromine going towards the positively charged carbocation. And so that attaches there, and then our mechanism is complete and we've formed our product. And our product is what we call a dihalogenolcane. It's called 1,2-dibromoethane. So we've started with an alkene and we've basically added bromine onto it, but I've been showing it step by step using this mechanism. So that's the first mechanism. So basically what we've done, we've added the electrophile on to the alkene, and that's why it's called electrophilic addition, because you're adding it on. You're not substituting anything, you're adding it onto the molecule literally by breaking this double bond. So that's the first one that you need to be aware of. Now the second one, the fact that was halogenation, where we add a halogen. The second one, what we're going to do, we're going to be adding a hydrogen halide. Now we'll stick with ethene again and do the same mechanism. I'll draw it a bit bigger. So if we have ethene, and this time we're not going to have bromine, but we're going to have a hydrogen halide. So we're going to have hydrogen bromide. And so if we start again from the whole mechanism, what's going to happen is, in this case, you've got hydrogen and bromine. Now bromine is more electronegative than hydrogen, and so bromine will push its electrons towards itself, leaving hydrogen the one which has less electrons. So in other words, hydrogen is slightly delta positive and bromine will be left delta negative. Yep, and so if we redo our mechanism, we have an arrow from the double bond going towards the hydrogen, as that's where it'll go to donate its electrons. That will cause this bond to break. Again, make sure double-headed arrows. Yep, so that's the first step, and then we can draw a carbocation. Remember, the double bond always breaks, so we will withdraw that. We'll put H on there, and then this will be a carbocation, and that will be a Br molecule with a negative charge and a lone pair of electrons. The next step, we'll have an arrow coming from the lone pair going to that carbocation. Yep, giving it that fourth bond back again, and that will form the molecule, which in this case is just going to have one bromine on it, and so it's going to be called 1-bromoethane, because in this case it only has one bromine. We've basically only added one Br to it, and then an H as well, and so we formed a halogen alkane with one bromine. And so in this case it doesn't really matter which carbon you draw the carbocation on, because either of them are the same. As you can see, it's a symmetrical alkene, and so either of them, it doesn't really matter. Now the example I want to show you now is a bit more complicated because it's what we call an unsymmetrical alkene, and so another rule applies to it because it's a bit more complicated, as you have to be careful about which carbon we draw the carbocation on. So my third example I'm going to draw for you, it's the same process, adding a hydrogen halide, but this time with an unsymmetrical alkene. So in this case, instead of using ethene, oh great when your pen stops working. So in this case, instead of using ethene, we're going to use propene. So we're going to have propene, which looks like this. H, and then we're going to be adding hydrogen halide, which is HBr, the same thing. So our first step is, again, like we explained before, the hydrogen will have a slightly delta positive and the bromine will be slightly delta negative. And so what will happen is we'll have an arrow going from our double bond towards our hydrogen, and then that will break this bond, and that's the first step. Now this is the hard step where we have to get our head around what happens here, because it's very easy to confuse where we put the carbocation. So I'm going to show you both examples. So we're going to have two ways we can do this. So in one case we're going to have CCH, H, and then we've got CH3 there, and H. So one example, we can put the hydrogen here and put a carbocation there, or we can do this. If I just quickly draw this molecule, CH3, we could put the H here and the carbocation there. Now, the way this is explained, and in terms of choosing the right one, is by a rule called Markovnikov's rule. Now, Markovnikov's rule states that the hydrogen will attach to the carbon which has the most hydrogens attached to it already. So as you can see in this case, if we attach it, so if we just ignore the hydrogen there, if we attach the hydrogen to this carbon, we have one hydrogen attached. but if we attach it to this carbon, it's got 2 hydrogens attached. So Markovnikov's rule would follow that this is the correct one, because this carbon has more hydrogens, so it's right to attach it here. However, this carbon only has 1 hydrogen, that carbon has 2 hydrogens, so it should attach to this carbon. Now, that's a rule, you can follow that, but in proper terms, I'm going to explain it about why that is, and that's because of the inductive effect. It's called the inductive effect. And it's about the carbocation being stable. Now what it is that this carbocation is attached to 2 carbons, as you can see. And what that does is, that carbon is missing a bond, and it's lacking those electrons. And so what these carbons do, they push electron density towards it. So in other words, it's called a positive inductive effect, because inductive effect is all about having surrounding carbon groups that push their electron density towards the carbon. So they're like pushing their electrons towards this carbocation, which is slightly unstable because it's missing a bond. So in this case, what we've got a secondary carbocation. So a secondary carbocation. And that is purely because on our carbocation we've got 2 carbons surrounding it which are pushing the electron density. In this case, we've got a primary carbocation, because as you can see, the carbocation is only attached to 1 of the carbon. However, in this one, the carbocation is attached to 2 carbons. So there it's attached to 1, that's attached to 2. So therefore, this is the one that we're going to choose, because in that case, the carbocation is going to be more stable, because we've got more of those alkyl groups or carbons which are pushing their electron density towards the carbocation, and that's what makes it more stable. However, this one is going to be less stable because we've only got 1 carbon pushing it. So therefore, this one is not the one we're going to use. We're going to be using this one, and that's because of the inductive effect. So the carbocation formed has got more alkyl groups surrounding it. So that's the one we choose. So then if we complete the mechanism, we will just have obviously our Br, which we've just followed through. I'll just use that. We have our Br here. And then the same thing, we just make sure arrow from the lone pair going towards there, and then that will form, and then our product will be C. And so in terms of naming that, if we look at our carbon chain, it's going to be 2-bromopropane. Yep, and that is electrophilic addition, and that's the reason why we form this product and we don't follow through on that product. So I hope you understand the mechanism, I hope it makes a lot of sense, and yeah, just make sure we follow through on all the arrows, just like I have done, double-headed, and also make sure you include these dipoles as well, as they're very important, and the way I've drawn the mechanism here is what you need to get full marks. So you'd have to be drawing that arrow, this arrow, that arrow, all the lone pairs, and that's very important. So I hope this really helped, guys. Please like and subscribe, and leave any comments in the section below if there's anything else you want me to go through. Thanks a lot, see you soon.